Semantic proofs. Semantic proofs, also known as tableau methods, are among the most effective and easiest to use. In a semantic proof of A, we show that the negation not A of A is not satisfiable by building a so-called semantic tree for not A and observing that the tree closes, as we say. The closing of the tree implies that A must be a tautology. Intuitively, the closing of the tree means that all alternatives for satisfying not A have been checked and found impossible, so A must be a tautology. A semantic tree for a formula A codes a contemplation on what else must be true if A is true. For example, if A conjunction B is true, then A and B must be true. So we write them underneath A and B. Respectively, if A or B is true, then A or B is true, but we do not know which, so we split the tree at this point into two branches, one for A and the other for B. The rules for forming semantic trees follow the idea that we write underneath a formula whatever immediately follows from the formula in view of its main connective. For each connective, except negation, we need two rules. The rules are as follows. Disjunction rule. We have seen this already. The tree splits to the two alternatives A or B. For the negation of A or B, we write both negation of A and negation of B underneath the formula, because for A or B to be false, both A has to be false and B has to be false. Conjunction. We have already seen the first rule for conjunction. The rule for the negation of the conjunction splits into two possibilities, not A and not B, because if A and B is false, it means that it is not true that they both are true. So either A is false or B is false. Negation, we have only this one simple rule that below the double negation of A, we write A. Implication. If implication is true, then as we see by simply glancing at the truth table, either B is true or not A is true. So the tree splits here into not A and B. If the implication is false, which only takes place on one row of the truth table of implication, then A must be true and B must be false, so we write them underneath the formula. Equivalence. The equivalence means intuitively that A and B are both true or both false, so we split the tree into two possibilities. In the first possibility, A is false and B is false, so we write negation A and underneath negation B. The other possibility is that A and B are true, so we write them first A and then underneath B. The negation of equivalence means that A and B have a different truth value. So either A is false and B is true, that's the leftmost branch, or A is true and B is false, that's the rightmost branch. A branch of a semantic tree is closed if it contains both B and not B for some B. A semantic proof of A is a semantic tree for the negation of A in which all branches are closed and in which all the rules that could be applied have been applied. The semantic proof demonstrates that A is a tautology by showing that the assumption that not A is true leads to a contradiction, namely that both B and not B are true for some B.